Good evening, everyone that is watching. This is a secure network architecture design presentation by myself, Alan Muhendo. This is an example of a corporate infrastructure diagram. It contains firewalls, routers, switches, which have different departments connected to them. It contains a proxy server and an email server, which are connected to an intrusion protection / detection system. It contains an air-gapped department, the research and development department. So the two routers, router 1 and 2, connect the internal network to the internet through firewall 1. The four switches, switch 1 through 4, are in the DMZ network for network segmentation. The 5 separate departments are shown, which could be, for example, sales, HR, IT, accounting, and marketing, with a minimum of 25 clients each. This drawing also includes a demilitarized zone hosting the proxy server, email server, DHCP server, intrusion detection system, and the intrusion prevention system. It also includes an air-gap system for the research and development department to ensure maximum security and isolation. It has two firewalls, firewall 1 and firewall 2, for additional security between the internal network, the DMZ, and the internet. This infrastructure design provides network segmentation, security, and the required components for a corporate environment. Discussing security issues and implications of advanced and novel networks and protocols. Networks like software-defined and network function virtualization, 5G networks, intent-based networking, and quantum networks and post-quantum cryptography. Security implications related to software-defined networking include the centralized control plane in SDN can become a single point of failure, and this can become an attractive target for attackers. Virtualization of network functions introduces additional attack surfaces and potential vulnerabilities. Proper isolation and segmentation of virtualized network functions are crucial to prevent unauthorized access and data leakages. So to deal with this, we can implement strong authentication and access control mechanisms for the SDN control plane. We can regularly update and patch SDN controllers and virtualized network functions to address the known vulnerabilities. We can also employ secure communication channels and encryption between SDN controllers and data plane elements. Security implications related to 5G networks are increased bandwidth and low latency of 5G networks enable new attack vectors and faster propagation of threats. The massive Internet of Things deployments in 5G networks expand the attack surface and introduce vulnerabilities in resource-constrained devices. Network slicing in 5G creates isolation challenges and potential for cross-slice attacks. To deal with these problems, we can implement robust authentication and encryption mechanisms for 5G networks. We can employ secure network slicing techniques to ensure proper isolation and prevent unauthorized access between slides. We can also implement security measures at the edge, such as firewalls and intrusion detection systems, to protect IoT devices. This drawing illustrates the security threat landscape in 5G networks, where we have illegal intercepts from fake base stations, we have DOS attacks, we have privacy breach, we have flash traffic, slice and resource theft, threats originating from the internet, and security policy conflicts between operators. Security implications related to intent-based networking. These include automated network configuration and management in intent-based networking can lead to unintended security misconfigurations. Malicious actors can potentially manipulate intent declarations to compromise network security. The lack of visibility and control over automated network changes can hinder security monitoring and incident response. So how do we deal with these problems? We can implement strict access control and authentication mechanisms for intent declaration and modification. We can employ machine learning techniques to detect anomalous intent declarations and network behaviors. We can also integrate security policies and constraints into the intent-based networking framework to ensure compliance. Quantum networks and post-quantum cryptography. Quantum computing poses a significant threat to current encryption algorithms, rendering them vulnerable to quantum attacks. Quantum key distribution offers enhanced security for key exchange, but requires specialized hardware and infrastructure. Migration to post-quantum cryptographic algorithms is necessary to ensure long-term security against quantum threats. How do we deal with these issues? First of all, develop and standardize post-quantum cryptographic algorithms that are resistant to quantum attacks. Secondly, implement hybrid encryption schemes that combine classical and post-quantum algorithms for backward compatibility. And then we can establish quantum-safe key exchange protocols and integrate them into existing network security frameworks. Below are the references used for this work. Thank you very much.